Let me show you how to be a good Bayesian.
Hello, my dear Bayesians! For this episode, I am thrilled to be back on stage for a live show at Imperial College, London. Thanks to the great Oliver Redman, we were able to assemble a dream panel, there is no other words, with 3 pioneers who spend their days wrestling with one deceptively simple question: how certain are we about our deep learning predictions? In this conversation, you will hear Dr. Mélodie Monod, Dr. François-Xavier Briol, and Dr. Yingzhen Li talk about why Bayesian deep learning is blossoming and why it still gives even the brightest statisticians a few gray hairs. We'll explore diffusion methods for richer posterior estimates, debate whether marginal likelihood really deserves its spot on the model selection pedestal, and dig into the trade-offs between exploration and exploitation in reinforcement learning. You'll also get a candid look at the computational headaches that come with scaling Bayesian neural networks, plus fresh ideas for baking uncertainty into large language models. Just a note, there is no video for this episode as the conference room wasn't equipped, so this one, folks, is an old school podcast episode, just audio in your earbuds. This is Learning Bayesian Statistics, episode 138, recorded live June 24, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com. Welcome to Learning Bayesian Statistics. Thank you. Good crowd. Very spontaneous applause. I love that. So welcome to a new live Learning Bayesian Statistics episode. Thank you again so much to Oliver Redman for setting this up. We're going to talk today about a lot of uncertainty quantification. But first, I always love to know a bit more about the guests and what they're doing, how they ended up doing that. Also today we have a bunch of students here, so I think it's also very inspiring to know that you're not just a title and a diploma, but how you ended up here and why you're doing what you're doing today. So let's start with you, Yingzhen. How did that happen? What are you doing today, and mainly what was your path?
Yeah, so thank you for having me. So I'm Yingzhen. I'm currently an associate professor at the computing department at Imperial College London, and I do machine learning. So I have an interesting path going to the Bayesian statistics and machine learning. So at the beginning, when I applied for my PhD, I wrote in my proposal saying that I want to do deep Bayesian machines for natural language processing applications. Right, so you see, this is a pretty machine learning like NLP and also non-Bayesian at all. But in there is a central question, right? So the deep Bayesian machine there, they have a very complicated normalizing constant, which also shares, right, with the Bayesian inference path, right? In the posterior, we also have a very complicated normalizing constant that we cannot compute. That's essentially why we need to invent a lot of different computation techniques, Okay, so yeah, I went to doing my PhD in a lab in Cambridge that probably is one of the most Bayesian lab in the UK. And then I got into this Bayesian modeling world, but I still have this interesting question about how to efficiently compute the samples or compute the normalization constant from a intractable distribution. So I did my PhD purely on this approximate inference problem. But I still have this machine learning thing in mind, right? So most of the things that I do within the modeling side is related to neural networks and also how to apply Bayesian methods to neural networks. Yeah, so after that I went to industry, basically gained some interesting application experience, and then came back to academia. Nowadays, I'm doing essentially still machine learning, deep learning with generative modeling and language models, but I still want to ensure that some kind of Bayesian statistics or computation ideas can be applied in that case.
Okay, yeah, fascinating. I really love seeing these paths and seeing that it's not always linear. Also, is very important, I think. Melody. So let's get with you. And like, I want to say that apparently we're a majority of French speakers today in the panel. This was purely random. Like, this was not planned at all.
You think?
Yeah, well, I think it's just a reflection of how superior we are. But like that's. Melody, yeah, let's go with you.
Yes, thank you so much. Thank you very much for inviting me. So I'm a senior postdoc researcher at the University of Oxford, and in terms of my path to come here, I did all my education in statistics. So statistics really defines the core of how I think. And, I felt in love with statistics and decided to continue through it. So for me, statistical principles really govern what I do and how I do it. And so I really mostly think about how machine learning tools can help us solve problems in statistics than the other way around. So I did my PhD in statistics at Imperial, finished in 2022, and I was supervised by Dr. Oliver Ratman and Professor Samir Bhatt. And during this PhD, I was very grateful because I got to work on both applied statistics and more methodological statistics. So in the applied side, I got real-world experience on working on Bayesian models and methods for estimating dynamics of infections of COVID-19 and HIV. So this was really interesting work and really taught me a lot about how to design statistical models and the real challenges that one can face. But I also did some methodological part on more functional prior on Bayesian statistics and some non-parametric statistics as well. Then I did some work in the industry, and this is when I started to be interested in building models with deep learning, so with neural networks, but in a Bayesian way. So retaining the uncertainty, the interpretability, and the robustness that brings the Bayesian inference. And so now I'm a postdoc, and my work is really about trying to, again, merge those two ideas. So try to use deep learning ideas to enhance the Bayesian inference, so being able to accommodate new data modalities or high-dimensional data, but again, retaining all the good Bayesian principles.
Damn, yeah, that would be absolutely fantastic, and we're definitely gonna talk more about these topics right after the intro round. But FX first, yeah, a few words about your background.
Yes, thanks for having me. So I'm, as we've said, an associate professor in stats at UCL. So at UCL, I basically lead a group which is somewhat in between stats and machine learning. So, and I've been doing this for a little while now. In terms of my background, I actually started kind of my education thinking I wanted to do maths, but there wouldn't be many jobs for me doing maths. So I decided to instead do math, stats, and economics. And then basically I found out that stats is a lot less boring than most people think. And so, yeah, I guess I really liked it during my undergrad. And so for me, it was, something I really enjoyed doing it. So let's let's go for it. So I did my PhD in between stats and machine learning, and that's kind of how things got to this point. I guess in terms of what I do, I would say it's mostly kind of thinking about computational aspects of Bayesian statistics. And I'm someone that really likes to kind of steal ideas from other communities. So I during my PhD, for example, I spent a lot of time at purely mathematics conferences. In terms of my publication record, it's kind of in between stats and machine learning. And what I like to do is kind of look around and see what's interesting and what's good for my problems. Yeah, I think that's about it.
Yeah, thanks. And yeah, very broad presentation out of that. That gave me a lot of ideas for follow-up questions. Yingzheng, let's start with you. I'd love to talk about what you're currently doing right now. So if you could maybe take an example of what you're currently working on, and maybe tell us about the challenges you're facing, how you're addressing them, and where you're hoping to take the project.
Yeah, so as I said, right, so we've been doing quite a lot of different things about applying, Bayesian computation or probabilistic inference techniques to various generative modeling settings. So maybe one thing that is relevant here is about, quantifying uncertainty in neural networks. So one thing that we can see right now here is we have very amazing chatbots and other kind of generative AI models around us, like ChatGPT, Gemini, or Claude, right? So those are giant neural networks trained on tremendous amount of data, right? So that's how they gain their sort of like a power of doing all these intelligent things. So then the interesting question here is, do we still need to quantify uncertainty, right? Well, in this big model, right? So that is actually a very interesting question, because around maybe 10 years ago, when the neural networks are bigger than traditional statistical model, but still not too big at this scale, right? We can still ask the question about, okay, if I train a neural network on, some image data set, should I also quantify uncertainty based on, okay, the image that we haven't seen or some other edge cases, right? So that's how this interesting field of Bayesian deep learning got popular again, and people, including myself, have research on various Bayesian computation methods, efficient computation methods, on how to train what is called Bayesian neural networks, where you can think about it as a neural network, but you treat the weights of the neural network as a random variable, and then you put a prior distribution over it, and you do the Bayesian treatment to get the posterior, right? So there has been a lot of development there, but going back to nowadays, given that this model now we have for language model is so big, and presumably they have already trained on the entire web of the data point, you might thought that, okay, there might not be any leftover unseen data point that might not be interesting at all, right, in terms of uncertainty communication, and there has been computational challenges of doing that. So, but now people also start to think about, okay, can we do this kind of Bayesian techniques in the fine-tuning procedure, where you're going to fine-tune your pre-training language model to some, say, domain-specific data set, or whether you can even do this kind of uncertainty communication when you're just trying to prompt your language model with some instructions, whether the language model can understand. There might be some uncertainty or some ambiguity beyond the prompt that you provide to the language model. So this actually opened up some new avenues for Bayesian methods applied there, and we are actively researching on that domain.
Yeah, that's absolutely fascinating. And Melody, that makes me think a bit about what you said you're working on in your introduction. So how wrong am I to think that? How related is your work?
Yeah, it's very related. So I'm not working on large language modeling, though, but it's very related because, as I said, I'm kind of Bayesian at heart. So for me, it's really, as I said, using machine learning tools to enhance Bayesian statistics, and of course, Bayesian neural network, as you just talked about, are really in the middle of all of this, because in deep in Bayesian deep learning, Bayesian neural network are kind of ominous, right? So I think for me, what I'm really interested about is to be able to build Bayesian models. So when I say Bayesian models, I really mean think about it as really a Bayesian hierarchical model. So from all the connection with maybe multiple data sources, maybe multiple response, maybe layers of parameters, maybe functions and functional pairs with it. Think about it as like a complex model, right? But in it, you want to be able to accommodate covariates, which are non-structured or very high dimensional. So for example, if I give you some MRI data and some genomics data of a patient, can you predict the 5-year survival? And so I'm really interested into being able to do this, but with uncertainty quantification and not like an ad hoc uncertainty quantification, but actually a real Bayesian inference and a real uncertainty quantification that, is both aleatoric and epistemic. So that's what I'm interested in. And you mentioned about maybe a recent project. Just to give an example, is with a collaborator at Imperial and the University of Copenhagen, we recently released a preprint, which is about deep survival analysis. So this is really a survival analysis model, but in it you have a neural network that models your hazard. And this allows you, again, if you had my MRI example, to use a neural network which has the inductive bias that you want, because there have been a lot of empirical studies that have shown that, say, a convolutional neural network could have a correct inductive biases. So you can leverage this rather than using another, another prior that you don't really know how it informs what. So this is what we've developed, and I think for me the 3 main characteristics that I would like to, what I aim to go to is really having models that are both principled, so you can have a prior specification from expert knowledge, and this is really hard to do in deep learning, as you just mentioned. You mentioned the prior and the weights, but the problem in deep learning is that the expectation of a neural network is not known in closed form, given that the weights are stochastic. And this is exceptionally complicated, because then you cannot resonate in terms of, I'm going to place a prior because I know that my expectation is going to be this value, because you cannot have the expectation. So being able to specify a prior is very challenging and one of my interests. Then of course being able to do inference, which is not easy when you have big data. And lastly, theoretical guarantees. So we might talk more a bit about the tools that are available, but for now there have not been theoretical guarantees that an uncertainty of in neural network were quantified were actually the uncertainty of the true posterior.
Okay, yeah. Thanks, Melody. If indeed, lots of questions for you in a few more minutes. But first, ethics. When we were talking before the show, like Injang and Melody were telling me, well, basically what we do is kind of like trying to get Bayes into machine learning, and since you're French, you're contrarian, and so you said, no, I do the contrary. I do machine learning for Bayes. So of course I'm summarizing here, but yeah, can you maybe tell us what that means for you? What would that mean to try and use machine learning tools to include that into Bayesian models?
Sure. So I guess my first contrarian point is that I'm actually Belgian, not French, which is but so this is the most important misunderstanding of this.
Yeah, I mean, I don't know. That was very French of me. So that was on point.
You have a strong prior.
Yeah, I guess we did discuss this before the start of the podcast, but actually I think I resonate with a lot of things that Melody just said. So for me, the kind of difficulty with being Bayesian about machine learning is that there's a lot of quantities that it's actually really hard to put priors on, right? So we've talked already about the weights of neural networks. This might be something that's well accepted in the machine learning community. If you go to a statistics department and you tell them that I'm going to put, priors on weights of something very complicated, people are going to start to worry, basically. And so to me, the advantages of Bayesian deep learning, and maybe Yingsen will disagree with this, and maybe this will be the kind of topic of this panel, but basically having stochasticity on some weights of a neural network provides something else. It doesn't provide uncertainty in the same way that, you would typically expect from a Bayesian model. So if I have a, important scientific problem with an important quantity of interest that I want to recover, it's kind of a lot more clear what you should do, right? You place a prior and you're going to try to update that with data. Here, actually, in the weights of a neural network, no one cares about the weights of a neural network, right? So really, it's a way of kind of providing stochasticity, and that might have some advantages, and I'm sure Yingsen will kind of tell us a lot about that much better than I could. But it's really quite a different task. So I guess what I meant earlier when I said I'm kind of more into kind of using machine learning for Bayes is more that the sort of thing that Melody was talking about. So, like maybe you have a very complex model, and actually, part of that model is kind of you want to have some more flexibility in there, and then maybe using some sort of machine learning method in that part of the model kind of makes sense. But I'm still very interested in kind of the sort of techniques that, Bayes was originally for, or at least, that for many, many years, statisticians have focused on, which is kind of like caring about uncertainty of parameters that are kind of meaningful in some way, in some kind of fundamental way. So just to give some examples, so one topic that I've worked on is simulation-based inference. So that's one of the areas where I work on now. So they're really kind of, where the field of machine learning has brought a lot has been in giving very, very flexible conditional density estimators, essentially, that can act as essentially surrogate for a likelihood which might not be available to then allow us to do Bayes. And, here all we need is really something that, a very, very flexible model that can essentially approximate any density. But we're not actually using, being Bayesian about the parameters of that model. We just use this as a surrogate to then be able to do Bayesian inference about certain parameters we care about. And to me, this is like, obviously, I don't need to kind of say much about how much machine learning has changed things in recent years, but clearly, there's a lot of things that statisticians could take, and I think it's, slowly starting to happen. So, only a few years ago, I don't think statisticians would have even considered doing something like this, whereas now it's becoming much more accepted. And I think that's the sort of thing that we're going to see more and more of in the future.
And how, like here, for instance, in this case, if people wanted to do simulation-based inference, what would you recommend? What tools would you recommend someone look into to actually do it implement it in their research or project?
So you're talking about more like programming tools?
Yeah, exactly. Yeah.
Okay.
Or
so,
open source software, stuff like that.
Yeah. So I mean, there's a bunch of packages, and I'm not gonna take one suggestion.
Oh, yeah, you can name a bunch. And
I don't want to get in trouble with.
That's fine. You can name a bunch, and then we'll add them to the show notes of this episode.
Yeah, so
but I know people interested in that. They usually go to the show notes and then try to see what would fit more their project.
Yeah, so there's a bunch of packages that people use. There's the SBI package, there's Bayesflow. I have to admit that usually I leave my PhD student to do a lot of that. So I'm not the best qualified to actually do this or talk about this. But yeah, so there's a bunch of different tools that exist out there. And I think, that's also partly why it's being picked up a lot. So actually, if I look at, the problem of simulation-based inference, so maybe I should have explained a bit more what that is. So it's basically when you're trying to do, let's say, Bayesian inference, since we're in this podcast. So you're trying to do Bayesian inference, but your model, you don't have a very good handle on it. So what you'd normally need to do Bayesian inference is a prior and a likelihood. And you might have a very good prior, but maybe your likelihood is actually very hard to write down in closed form. You cannot evaluate it. And so you cannot do Bayes as you would typically do. And so there's been, many methods that have been proposed in the literature. One of them is called approximate Bayesian computation, and that's been around for the last 20 years. And actually, very recently, these new methods that I've just talked about came in. And, the only reason that statisticians are now paying attention is actually because a lot of the practitioners actually use these kind of more machine learning methods there, and they really like them, right? So, for example, I've recently started collaborating with a cosmologist at UCL, and when we first started talking about the problems that he's trying to work on, which relate to kind of dark energy, when I suggested he use some ABC method, he really kind of just laughed at me, basically. And for him, like the advantage of these newer methods is just such that he wouldn't even consider going back. And so I think now kind of statisticians are catching up. And part of the reason that he's really into this is because there is lots of software out there that's kind of allowing that. I don't want to say that there's no software for ABC. There is also, but I think part of the reason has been that, really.
Yeah. I mean, and that's why I always ask these question based. Like, I'm myself much more of a practitioner than a theoretician, so it's always like, and that's also the way I learn. Usually, it's just like going to the website of the package or else reading the tutorials, trying the code for myself, reading the code, and I guess that's also how a lot of people use these tools, because they need to use that in their projects. So having an open source software somewhere that helps you to do that is very important. So yeah, we'll definitely link to a bunch of those in the show notes. If you guys want to hear more about simulation-based inference, we have a bunch of episodes already on that. So you go to the website, and we have a keyword tool. You just look for that, and you'll see a bunch of episodes. Yingzheng, yeah, I'm actually curious. Talking about tools, the kind of problems you were talking about. How would people do that right now? Is that even something that's possible to do? Because I remember I had Vincent Fortwin on the show a few months ago, and he works a lot in Bayesian deep learning. And I asked him this question, like, what would people do if they wanted to do some Bayesian deep learning in their project? He was making the point that this is still a very active area of research, so there is no go-to tool to do that. That if you want to do the classic deep learning, it's actually super easy, especially in Python. You just fire a PyTorch or something like that, and that's super easy. But the probabilistic deep learning part is still challenging and can be hard. So yeah, I'm curious. Now we're a few months later. There is a lot of progress going on in that field. So I'm curious how you see that and what you would recommend people do.
So that's an interesting question. I think indeed in the machine learning field, right, when we do the research and trying to implement new methods, we go to basically these tools like a PyTorch or JAX or like even TensorFlow, but they are like these tools that are specifically designed for just the neural network research, right? They are not designed for saying, okay, we do probability inference, right? I think there are some interesting problem right now in terms of why we haven't got very good tools. I mean, so if you look at the usual probability programming tools like Stan or like Turing or some others, right? So they are actually quite good in terms of like they have a more or less preferred inference engine. For example, like I think Stan usually use HMC, and there are some other programming languages use some other tools. But in deep learning, I don't think there are, especially in Bayesian deep learning, I don't think there is a agreed inference method. Pretty much because the neural network, Bayesian neural network procedure is also very difficult to compute, right? So people are still trying to figure out whether I should do Laplace approximation or whether I should do inference of what sense, right? And whether I should do stochastic gradient NCMC. So there is no sort of like unified agreed tool. And also, it's just, the difficulty of training Bayesian neural networks also, intertwined with the difficulty of training neural networks itself. Because at the end of the day, Bayesian deep learning methods are still using this idea of gradient descent. optimization with stochastic gradient descent as a major tool to perform the inference. So it's unclear to us whether we already have a very robust computational tools that we can agree on and then build packages on that. I mean, that said, there has been efforts, right, trying to make a wrapping package around Bayesian deep learning and just let users to use it like how people use Stan, right? So I think there has been some development for trying to do a Laplace approximation with Bayesian neural networks. That's Alex Immer and also his colleagues from ETH. So back in my time at Microsoft, right? So I also try to make a little tool that tries to do a various different version of Bayesian inference. So that definitely works for me, right? But that wasn't flexible enough to support the general applications. So yeah. Nowadays, if you look at applying these things to, let's say, language model, either fine-tuning or like in-context learning prompting, right? Then another challenge is to adapt Bayesian methods to the underlying language model that you're going to use. And for different open source language model, they might have slightly different configurations, which also means that your Bayesian computation methods also need to adjust to that. Otherwise, you won't be able to get very good results. So that also raised another challenge in terms of having a unified software for Bayesian deep learning.
Yeah, for sure. And I'll have a question for you about that, like uncertainty quantification and LLMs in particular. But first, Melody, I wanted to ask you, because as you were saying, you do a lot of theory, but you practice a lot. Also, you build models. So I'm curious. Now that we've established that uncertainty quantification is hard, and that's why you guys are working on that. What new methods do you see as offering meaningful gains in that realm?
Yeah, it's a good question. I think to me, recently, I think there's been a new, I think for inverse problem at least, or like for the topic of our discussion, which is you have some response and some covariates, there have been this whole idea of using diffusion methods and score-based methods. So in this one, you really can kind of integrate high-dimensional data. And what you need to do is kind of learn the score of your likelihood and your prior, and you can kind of sample from your posterior. So it's another way of sampling from the posterior. So you were talking about Stan, for example. Stan's samples from the posterior using HMC. In variational inference, you're going to approximate your posterior, where diffusion sampling and diffusion methods can be used to also sample from a posterior. And I think this is, to me, this is a really interesting new type of method. But there are still a lot of work to do to be able to use it in practice. To mention a few, so for now, there cannot be integrated in kind of hierarchical models. So when you have a hierarchy in your parameters, or if you have different data sources, they are quite hard to fit. So they are on top of being computationally hungry, it's hard to fit them and to make them work in practice. And they are not adapted to any likelihood. So you cannot use any data, any response that you would like. So there's still a lot of work to do to be able to use it in pipelines, in applied research. But yeah, I see it as one good maybe option for the future. And at least there's like a tremendous amount of work that is being done on the subject right now. So it's very exciting.
And how do you do that? Like, I'm really curious how concretely that looks like when you're working on that kind of things.
You mean how the method works, or?
Yeah, let's go with that. I meant something else, but actually I'm very curious about No, I was meaning, like actually what programming languages you use and so on. But I think going into the methods first is going to be more interesting.
I will try to do everything simultaneously. So the methods, it use diffusion dynamics. So diffusion models is a model where you kind of integrate noise to your data and then reverse back. So you kind of learn data from noise. And in the case of inverse problems or problem, when you have a response and some output, you're trying to learn your response given some covariates, right? So yeah, this is in a few words how the method work. But then the key point here, and I think this is what I'm going to say, is just that you need to learn the score of your posterior distribution. So this is the derivative with respect to your output of the logarithm of your posterior density. And so for this, you often need to have neural networks to learn the score of your prior and the score of your likelihood. And learning the score of the prior, there's a lot of now methods to do this. But learning the score of the likelihood is more tricky, and this is where a lot of area of research are focused on right now. In terms of fitting it, there's both code on PyTorch and on JAX that are available, that have been made available by Song, which is one of the main author in the papers that have been looking at this, or let's say the seminal papers. And the way you do it, to be honest, the code it's quite tricky. It's really not an easy pipeline where you say fit yx and then you get your posterior samples. Like, it's not at all to the point of Stan. I mean, Stan is so highly developed, but there's no community. There's no, it's really you in front of a GitHub repository having to figure things out. And as I said, the posterior, the sampling can be tricky. So you can obtain, NIN values. You can have things that are failings. It's really not. It's still really in the development stage. And of course, if you work with high dimensional data, you need to fit everything in GPUs, etc. So it's still tricky.
Sounds like you're describing my life. Ethics. I wanna give you time to talk a bit about generalized inference, because I was talking to one of your brilliant PhD students before the show, William, right, if I remember correctly. And yeah, he was talking a bit to me about these methods, and they sound very interesting. He mentioned spatial temporal methods and GPs, so of course now he had my curiosity. So yeah, can you talk a bit about that? I'm very curious about it.
Yeah, sure. So so I guess this would be what I spend probably the majority of my time thinking about. And I think it kind of links back also to the topic of the podcast, which is about uncertainty. So one thing that Bayes is really good at doing is doing uncertainty in terms of what can be represented for a prior and then perhaps updated, right? And typically with Bayes, you have to assume that your model is correct. So what I mean by that is, your likelihood, and frequentists don't like it when we say this. They also have to make some choices, right? So they have to pick a likelihood, and we therefore pick a likelihood. But obviously, when your likelihood is incorrect, well, actually, the posterior that you end up with is going to be potentially completely meaningless, right? Now, in practice, what most people do is they try to kind of make their likelihood more flexible, or have a more complex model, such that hopefully your model is complex enough that it can capture any sort of more complicated data generating process, and therefore you have something which is a bit more meaningful again. But this isn't always possible for kind of a range of reasons. So one reason might be computation. So we've already kind of talked about how one of the big challenges in Bayes is not so much. Well, of course, the modeling is hard, but it's really also the computation, right? It's having the tools. We've talked about tools, etc. It's how do you actually get a handle on your posterior? So if you kind of make your model more and more complex, just to kind of be able to kind of capture this data generating process, potentially what you're doing is you're making your life much harder, kind of computationally. And so I think what ends up happening, and you're much more of a practitioner than me, so maybe you can tell me if I'm wrong, but what typically happens is that people use simpler models, even though they sometimes know that the model isn't perfect, right? And the problem that we have with this is that, if we then use only the posterior as kind of our notion of uncertainty, and maybe that's then propagated to other quantities of interest, predictive distributions, et cetera, what we might end up doing is kind of being overly certain about something which is actually wrong, right? If my likelihood is wrong, then I'm going to be overconfident about my future predictions, for example, or about my parameter estimates. And so this topic of generalized Bayesian inference, there's kind of several names for it, but the idea is to kind of break away from exact Bayesian inference, and potentially in this respect get something slightly more meaningful and slightly more robust. So typically, one kind of approach that people take is they'll say, okay, well, I have some parameters that I care about. I have some likelihood, which I think is pretty decent, but I'm not fully confident. So what I'm going to do is, instead of starting with my prior and updating with my likelihood, I'm going to start with the prior, but then update with something else than the likelihood. And maybe if you've never heard of this, you might think I'm again completely crazy. But this field of generalized Bayesian inference basically says, well, there are other ways to condition on data, right? So if you're a hardcore Bayesian, you get drilled in your head from very young that the optimal way to condition on data is Bayesian conditioning, right? But this is obviously only the case if your model is correct. And when your model is not correct, it's not clear exactly what's the best way to update your beliefs. And so what we've been looking at, and my group, but actually there's a very rapidly growing community looking at this, is looking at what happens when you update with something else than a likelihood, and how should you update? What is then the meaning of this posterior? Could it potentially bring you some kind of computational advantages? So maybe you can pick some other way of updating that's actually then means that maybe I don't need to run Stan or something else. And what kind of robustness can you get? So I guess you kind of mentioned spatiotemporal modeling. So one recent work, which I guess I'll talk about William since he's here, has been involved in, is thinking about Gaussian process models. So I think that's a perfect example of the point I was making earlier. So basically, in Gaussian processes, one of the reasons that people love Gaussian processes is that everything is conjugate, right? So you start with the Gaussian prior. Okay, it's now a prior over functions, but it's Gaussian. You update with a Gaussian likelihood, and then you get a Gaussian posterior. Great. We don't need Stan. We don't need any of this, right? Now the problem is that if your noise model is not actually Gaussian, if the true data generating process is not actually Gaussian, but you use a Gaussian noise model, then you could potentially have a lot of issues, right? And I think a lot of people basically ignore this and still use the conjugacy because it's so convenient. Because if suddenly I have to start approximating a posterior over a space of functions, well, that's very hard work. And so some of the work that William and Matthias, another one of my PhD students, have been leading, is looking again at Gaussian processes and saying, well, how can I update in another way such that if my model is correct, I get something very, very similar to a standard Gaussian process. But if my model is wrong, say because my observation is partly corrupted, maybe I have some broken sensors, maybe I have some outliers in my data, then I don't get arbitrarily badly impacted. So for example, in Gaussian processes, you can show that even just one outlier can completely change what your posterior will look like. It's extremely sensitive to that. And so using something else than a likelihood to update, using a so-called robust loss function, can allow you to kind of essentially mitigate these sorts of issues. So essentially robustify your inference procedure. And so we've been doing this for Gaussian processes, but we've done it for lots of other things. So change point detection, Kalman filtering. We've done it for doubly intractable problems. We've done it for all sorts of problems that kind of statisticians or Bayesian statisticians care about. And just trying to think about how can I update in a way which is sensible from a kind of UQ point of view, but also kind of practical. So I think kind of going beyond classical Bayes can open a lot of opportunities, be it both on robustness or on kind of conjugacy. And I should say that, I should have said earlier when I was talking about this Gaussian example, the really cool thing about the work that William and my other student Matthias have been doing is that you can do robust Bayes whilst maintaining everything conjugate but being robust. And so basically you don't force people to pay a huge price for having this extra robustness just by changing a little bit how you update. And that's, I think, something which I hope more people will start looking at, and that's indeed the case.
Damn, so many follow-up questions. I didn't talk to you guys after the show, but yeah, I'm very happy to hear you say that not all the likelihoods are Gaussian. Because I personally never work with Gaussian likelihoods. I would love to, but almost all of my data is count data. So very often a GP. So you can do a GP on that, but it will be a latent GP. So that means you don't have conjugacy anymore. So HSGPs have changed my life, for instance, because now you can fit a GP in way less time than a vanilla one. But yeah, what you guys do sounds very interesting, and so yeah, send me also any links you have, and I think also the work we're doing on the PyTensor side, which is the computational backend for PyMC, could be interesting to you guys, because maybe we have done some stuff that you don't need to re-implement it, you can just build on top of that, and we will be very happy with that.
Yeah, so maybe just one point to kind of temper what I've just said. So one of the exciting things about this field is that there's lots of things to do. So, we're working hard on that. But for sure, one of the things compared to some of the other fields that we've talked about is that there's very little in terms of software packages.
Yeah.
So in fact, I say very little. There's, a bunch of GitHub pages and that's it. So I think that's clearly one thing which, going forward, now we're still developing lots of new methods, but very soon there's going to need to be a bit more of a push towards that for people to really take it seriously.
Yeah. I completely agree, because in the end, if you have a great paper implementing that, that's awesome. But then that means if you don't have the accompanying software, almost nobody will be able to implement that, because this is huge work, and you probably need a lot of math background, and just coding that up is extremely hard. So yeah, that's something I always try to be very careful about. That's something, for instance, Jesse Grabowski on the PyMC team and PyTensor team has been doing a lot. He does a lot of state space models. And for instance, one of the weird things is that doing Bayesian state space models, there is no real go-to software package to do that right now. And so he's been working a lot on the state space submodule of PyMC to try and be able to do that. So now you can do state space models in PyMC with that. We're still working on batching that. So that means, because most of the time when you're working on time series, you don't have just one. You have a bunch of time series that you're interested in, that you want to model in parallel, or even do some hierarchical pooling on that, because you're in the Bayesian world. And so we're trying to implement that right now on the state space module. Of course, it's a way longer PR than expected, as all the PRs, but we're getting there. So yeah, please send me a link we can put in the show notes. And Yingzheng, I want to ask you something as we're starting to close up the show. I'm curious, also a personal question, because since you work a lot on LLMs and with LLMs, do they know what they don't know? And if they don't know what they don't know, are we working on that? And is it even possible? How would we develop that?
Okay, maybe to answer this question, I want to first respond to one of the interesting points that FX made before about how stat community view about Bayesian deep learning, right? So it is indeed a bit crazy for the stats people to think about, the weights of neural network does not mean anything. Why should I put a prior on it, right? So I think the interesting question here is, in stat community, people talk about models. In deep learning community, people also talk about models, but they mean actually different things, right? So in stat community, people talk about models when they have a clear understanding about what are the interesting inference parameters that they want to estimate, right? Those parameters needs to have some kind of scientific meaning. But when deep learning people talk about models, they really mean predictive models. So I'm going to use statistical models and predictive models just to emphasize on the difference. And in the development of Bayesian deep learning, as well as how deep learning people use Bayesian deep learning, we really care about uncertainty estimation, quantification, decomposition, but in the predictive space. Okay, which means at the beginning, we already talk about predictive models. And going back to your question about whether the model know, it doesn't know, right? It's most of the case that is going to be evaluated again via prediction. Right, so it is difficult for people to say, oh, I just go into the neural network weights, just inspect on the neural network weights and say, okay, from the neural network weights, I know that this model does not know some concept. No, so it's usually when you plug in some kind of unseen test data to the neural network, and the neural network gives you some prediction. This prediction has some interesting, behavior or some bizarre behavior compared to like the in-distribution case that you start to know, okay, this model seems to know something that it doesn't know. Okay, so I just want to emphasize this point. So now the interesting question here is whether LLMs know what they don't know. Well, I think there has been some back and forth on this because it actually depends on what kind of uncertainty measure that you are going to put on the predictive distribution of these language models outputs. So there has been, non-Bayesian method, frequentist method for sure, and also some other ad hoc methods, right? Some of these papers show that, okay, indeed, when you test on out of distribution data, you have some interesting behavior that is different from the in distribution. So based on that, I say that my model can detect out of distribution examples so that my model knows when some point is not in their training data set. But some other uncertainty quantification method also show that this difference is not that clear. So I think it is still an interesting research question at the moment about truly assessing whether the language models know what they don't know.
Okay, yeah. And so actually a follow-up from that's coming from the chat. And thanks folks for putting in your questions. I can see them here. Basically, so you just talked about how can we measure the uncertainty of LLMs, and that person is asking, is this one of the causes of hallucinations of LLMs?
Well, I'm not sure. I mean, so I feel that the LLM hallucination, it depends on how you talk about it, right? So I don't necessarily see hallucination as a clearly defined concept. And when you define it as in some sense, generating some output that you haven't seen in training data, you might not know whether that is a good thing or a bad thing. Think about it. If you use, let's say, generative models like these very nice diffusion models of generating new images, right? If they actually generate, say, very nice looking and also, good content, right? Then you wouldn't necessarily call it hallucination. You will call it creativity, right? So hallucination is really that your model can learn to generalize to generate some unseen output, and that unseen output is something that is not well behaved. Then you call it some kind of hallucination, but it is not all kind of unseen output generation. They are all bad, right? And I'm not sure whether this is really like an uncertainty causes a hallucination. It's really just the model that can generalize to unseen output.
Okay. And so from what you're saying, I understand basically the fact of whether an hallucination is good or not is contextual on the answer. So like if it's hallucinating a bill, a text of law, that's quite wrong. But if the LLM is helping you writing a new mystery novel because it's actually able to make connections that you weren't able to, then that's awesome. So
that's contextual, indeed.
Yeah. Okay. So you don't want to get rid of that all the time, for sure. Okay. Melody, I think that one is for you because we have one asking about neural networks, Bayesian neural networks. So what benefits are there to Bayesian neural networks with weight priors over traditional neural networks.
Okay, so the question is, what's the advantage of Bayesian neural networks compared to neural networks?
Well, the question is, what benefits are there to Bayesian neural networks with weight priors over traditional neural networks?
Okay. Well, I think the advantage is that if you were to use a Bayesian neural network with weight priors, or there's also other priors that are available, just to say. But imagine you were to use weight priors, you would, assume some stochasticity on your parameters, and so thinking about Bayesian inference and Bayesian principle, you would try to kind of propagate this uncertainty throughout, and then build not only a point estimates of your weights as you would do with just a neural network, but you would have a posterior distribution on your weights, and so you would have uncertainty on the prediction that your Bayesian neural network could make. And so the advantage of this method is kind of the advantage of using a Bayesian inference is really about having uncertainty quantification in your predictions as well as your weights. But as Afik said, it's quite a weird a weird quantity to work with weights. So it's a bit hard to interpret what the uncertainty and the weights mean. So you would have uncertainty, and then you could have also robustness, and you could do multiple things with this posterior distribution that if you were to think about a research problem, a scientific problem, you could do counterfactual scenarios or things like this with uncertainty that you might not be able to do with just point estimates, or you would not be able to, communicate uncertainty to the decision maker. And in many cases, I don't think we talked about, specific cases, but in many cases, like in medicine or in epidemiology, uncertainty is really crucial to be able to make informed decisions.
Thank you, Melody. Yingjing, you wanted to add something?
Yes. So it is an interesting question about putting priors on the weights, right? So as Melody has mentioned, right, there has been other prior developments, for example, like try to directly put prior on the function space. So that has been something that I myself has previously also considered, right? But the overall problem here is that if you're going to put priors on the function space, you are maybe having a bit better in terms of understanding, but you need further approximations in the posterior computation. So nowadays, I actually view, putting priors on neural networks and computing posterior in a weight space as a convenient computational tool for us to reach this Bayesian inference in the neural network scheme, because I can do less amounts of approximation in the equations, and also I can utilize, what deep learning people have developed in terms of these nice optimization tools. The optimization tools for deep learning, they are developed for weights, not for directly optimizing functions. I can take advantage of deep learning methods to also, make my Bayesian neural networks work great. So yeah, I'm going to still defend for putting these posterior compute on the weights, but for a computational reason.
Okay, yeah, thanks, Yingjing. I think this one is for you, FX, and I like how it's phrased. This is purely on me. I'm sure that person is saying that on a purely neutral tone, but I won't. FX, what do you mean by wrong likelihood? If it assumes normal distribution, for example, is it when this assumption doesn't hold?
Yeah, so obviously, when you do kind of some sort of statistical modeling, so usually you assume that there is some sort of true data generating process, and you do not know a priori what this true data generating process is, but you're going to start observing some realization from it and hopefully kind of get a better idea of what that is. So typically what you do in statistics, and that's the case in, frequentist or Bayesian or all sorts of other settings, is you specify a, let's say, parametric model, for example. So where you're basically saying, I'm assuming that my true data generating process is one of the elements of that parametric model. Could be a non-parametric model, but just for simplicity, let's think of parametric models. And so your job then becomes to do parameter inference, i.e. try to recover the parameter such that if I pick that parameter, I have exactly my data generating process. So in the case of the Gaussian likelihood, basically what you're saying is, my data really is Gaussian. Maybe I don't know which mean or which variance, but I'm assuming that the data generating process is Gaussian. And obviously that might not be the case. So you could have a heavier tail distribution. You could have something bimodal. You could have all sorts of things where, regardless of which parameter value you pick, you're never going to recover the true data generating process. So this is what I meant earlier when I said, what if your likelihood is incorrect? Well, basically, what I'm saying is there's no element of my parametric family of distributions such that I ever recover ground truth.
Yeah, thanks. Great explanation. And so I know you've taken simple examples here to explain, for instance, like you actually have a heavy tail distribution and you picked a normal likelihood. So I know it's also something that's hard for students who start using the Bayesian framework when they have to pick a likelihood, so it's like, also, I don't want you to be completely scared in the sense that most of the time for most models, it's going to be fine if you pick, for instance, a normal and actually you have a heavy tail distribution. So for instance, you would need to use a student t distribution because you would see the model has problems in the predictions. So it starts to be a real problem when the model gets big and complicated enough. So if it's like you have a lot of GPs in your models, lots of interactions of a lot of covariates and so on, and then the model has like hundreds of thousands of parameters, and then you don't really know where to poke in the dimensions of the results. You need to look at different subsets of the posterior space to really see problems. So that's where I think your kind of work really enters. But for most of your simple models, it's going to be quite evident that the model is missing something, so they shouldn't be too hidden. So don't be too afraid. That's my main point. I have another question here. Maybe that's for you, Yingzheng, but you let me know. That person is asking, how can the users? Here. So how can the users use the uncertainty in real-world applications? How would uncertainty impact decision-making?
Yeah, that's an interesting question. So I think in the field of doing uncertainty quantification for deep learning, there has been a majorly speaking two type of applications. One is kind of like giving people warning, right? That as we discussed previously, that if we somehow can say, okay, so this model does not know this data point, or this data point is not in the model's training distribution, right? Then you might be a little bit worried about whether you can trust its predictions, right? So that you might be able to defer, let's say, the model predictions to an expert. I think this is actually quite important in, for example, like medical applications. So this is one way that you can use uncertainty in practice. But another way, which is also very exciting, is actually in, let's say, reinforcement learning, active learning, Bayesian optimization, and sequential decision making at the end, right? So you basically, maybe some of you have heard about some, recent hyped story about, okay, all these language model can do very complex reasoning because they are somehow, fine-tuned or trained on some reasoning data set with reinforcement learning. But then in reinforcement learning, a fundamental concept is something called exploration-exploitation trade-off. So what does it mean? It means that at the beginning, your model or your policy does not know anything about the environment, so that it wants to somehow start to first learn the environment by exploring. But as soon as you learn more about your environment, so then the model will become more confident, okay, in terms of describing how the environment behaves when I do this action. How would the environment respond to me when I do another action, right? And I'm going to start exploiting, right? So you can see that in this exploration-exploitation trade-off procedure, uncertainty quantification is key, because you need to let the model describe, okay, whether I'm confident that my prediction over the environment behavior is correct, whether I can rely on my prediction to decide, okay, what is the next action I'm going to do. So this is also a very important part how uncertainty quantification can be used in, for example, like this reinforcement learning setup, or like in experiment design setup, in active learning setup.
Okay, Okay, that's really fascinating. Do we have time for a few more Q&As? Okay, awesome. So let's continue. Great questions, guys. Thank you so much. You're a great audience. I have man, there are so many. Which one to pick? I saw one that was pretty fun. Oh yeah, here I'm curious about that one. Do you have any insight on how uncertainty quantification can inform decision making? And that second part was especially curious to me, especially when the decision maker is also another machine learning model. So that's like meta question. So yeah, like you have a model and you want uncertainty quantification in that model because you're going to make decisions based on the model's result, but it's not a person who's going to make the decision, if I understood correctly. It's another machine learning model. Does anyone want to take that one?
Well, I can try. So the previous kind of discussion in terms of this exploration trade-off, right, is in a slightly different setup as your the question, right? So it is the previous setup was the model itself will quantify the uncertainty of what has been learned so far and what is missing, right? And based on its quantified uncertainty, itself will make its own decision. Right. So it basically means that in this setup, the model who will make the decision will be the same model who makes this uncertainty quantification, so that you can somehow be a bit more confident in terms of guarantee that, okay, so if I made this decision of making this action, later on, I can use this action to update my model's belief again. Right, so you will have this kind of a consistent feedback loop during time. Now, I guess in terms of the other setup where one model provides uncertainty quantification, but then leave the decision to the other model, then I guess it will be a question about whether, let's say, the other model, right, can provide basically say the feedback to the uncertainty quantification model and also update its belief in a consistent way. I can imagine that if, let's say, this uncertainty quantifier model and the decision making model, they have different ways of updating their own beliefs. Okay, which means they don't have a sort of like a synchronized or agreed way to describe their own uncertainty. I can imagine there will be a gap, then you will have some suboptimal results.
Okay. Thanks for the input, Yingzheng. Melody, there is actually two questions for you. I don't know if I'll have time for both, but at least one. When you mention other Bayesian priors in neural networks, what do you mean? Training a network from Bayesian model simulation?
Yeah. So just to say for the other person, you can talk to me afterwards. I was thinking more about there's a whole field of functional priors for Bayesian neural networks. So the whole idea is, I mean, I'm going to talk about the aim more than the methods. The aim is really to be able to integrate expert knowledge decisions. So again, as we discussed before, having a prior on the weights, whether you put a normal or anything else, the weights are not interpretable. So you don't really know what you end up with, and being able to integrate some information or some prior that you have, some prior information that you have is really difficult. So the aim of those prior is to be able to, again, we were talking before about my example in survival analysis, if you wanted to integrate some MRI data and you had a good prior from previous clinical trials that your 5 years survival is going to be that point estimate with this uncertainty, you want to be able to have in your network which has this expectation and maybe this standard deviation on the prior when your weights or whatever you're placing your prior on follows the prior. So yeah, that's where there's some research on, and where I think it's really interesting, because I think the world of Bayesian inference is not going to be willing to accept neural networks because as I say, they don't know how to place a prior on it for now. So it's, I think it's a field that is worth continuing exploring.
Okay. Thanks, Melody. And yeah, the other one for you was related to survival analysis. So I encourage that person to come and talk to Melody after the show. There is a really interesting one that resonates a lot with my personal experience as a modeler. What are some ways that we can tell when a Bayesian model is too complex and there isn't enough signal in the data to update the priors? That's for whoever wants to take that. I can already start by saying like the easiest way is usually when you have a model, you kind of know there are some parameters which are hard to infer. Like if you're using GPs, usually the length scale is hard to learn. So that's the first thing you can do is comparing the distribution of the prior and overlay the distribution of the posterior. And there you can already have an idea. If your GP is able to learn both the amplitude and the length scale, that's really good sign because these two parameters are actually kind of related. So there is a weak unidentifiability between both. So that's why it's usually very hard for the GP to learn them. If the GP can learn both, that's really good sign that your model is able to, the posterior is contracting. But a lot of the time you'll see the length scale not contracting. I would say this is not too concerning because it's a hard parameter to learn. And usually you can have prior information about it. So what you can do also in these cases, you can fix the length scale to something that's reasonable, or maybe that you learned from a previous model, a machine learning model, and then you can use that as an input in your Bayesian model. So that's a very practical answer, but I don't know if you guys also have maybe a more theoretical one, but like usually what I do is that like a lot of plots. Like you need to understand how does the prior for that parameter work. And if you have some very important parameters in your model that really need to be learned because otherwise the model is not telling anything apart from, well, we think the structure of the problem is that one, then you definitely need to look at that parameter. If it's not learned, then probably the data are not enough for that model.
Yeah, and I would just like to add something. I completely agree with you. And I would just like to decouple some ideas. There's the model and there's the data you observed. And sometimes you have a data generating process, which is very complex. But if you have n equal to 10, you will not be able to learn the parameters of your model. So I think your answer is completely true when like you have not a lot of data. Maybe your data generating process is indeed a GP, but if you didn't observe enough data, you will not be able to learn the parameters.
Yeah. And also it depends a lot on the cover rates. I've had models which were working with some bunch of cover rates and then you add one cover rate and then that cover rate absorbs what the GP was saying and then the GP tells you there is nothing there. So that's not necessarily bad, but that's the data saying you something about the phenomenon you're observing. Jing?
Yeah, I just want to also bring up another point. So, theoretically speaking, so marginal likelihood is also another tool that you can use for model selection in general, right? So marginal likelihood basically says that you want to compute the log of PD, where it means that you need to actually integrate over the posterior. So, I mean, there has been this theory argument about this Occam razor in terms of like, trying to find the simplest model that can just fit well with your data. That is the principle, right? Now, the interesting question here is, okay, it sounds very difficult to compute, right? Because you need to integrate over your latent variable or the parameters that is already just a difficult Bayesian inference problem. And interestingly enough, right? So this model selection kind of marginal likelihood can also be approximated using some computation like Laplace method. And funny enough, in Bayesian deep learning, I personally think that Laplace method is popular not because of its sort of like very, say, superior predictive inference performance, but actually in terms of its behavior of very cheap computation to allow approximation to the marginal likelihood and also very robustly helping there to do model selection. So that's just my 2 cents. So you can try to think about marginal likelihood and see whether some interesting approximation like Laplace can help you.
Yeah. And when you're saying Laplace approximation here, would would something like INLA be useful here, or is it another approximation you're talking?
Well, I'm not sure about INLA, but I think it's just very easy that you first get the map solution, right, of your model parameters, and then you do this kind of Gaussian approximation around your map solution using this Taylor expansion. That's the very simple methods. There might be some computational techniques to speed it up, but I'm just referring to that principle.
Yeah. Okay, so it's like using a multivariate normal here to approximate the posterior.
Yeah.
Okay, yeah. So that's not exactly in lab, but that's like a simplified version. If you folks are curious, we have a version of that now in PyMC extras. So just pip install PyMC extras and you'll be able to use that. And there is active work being done right now with Google Summer of Code, who have a student in making the Laplace approximation and in-lab approximation also in PyMC better. FX, you wanted to add something on that, and then we'll ask one last question about LLMs, because there are two great ones here that I will merge into one, and then afterwards we'll call it a show, because there is only so much that a brain can take without coffee. So let's go with you, FX.
Yes, so I guess the first thing I wanted to do is be a little bit contrarian again. So in settings where your likelihood is wrong, which is what we were talking about earlier, the marginal likelihood is going to be a terrible way of doing model selection. Now, I think in kind of the deep learning, well, when you think about deep learning, in that case, that's much less likely to be a problem in the sense that I'm talking about, mostly because what we aim for is very, very flexible model. So essentially with very, very flexible model, you can pretty much approximate anything. So maybe not so much for this specific setting, but in general, you should be a bit wary about using marginal likelihood to make model selection, especially for smaller problems.
Yeah, very good point. So last question, probably for you, Ying-Jane, but guys, feel free to jump in. It's actually two questions. So is it possible to implement foundation models like LLMs with some Bayesian flavor? And then, is the training data for LLM from a single distribution? Like, how can we detect if a new input is out of distribution?
Cool. Okay. So I'm going to answer the first question then. So one of the biggest challenge of Bayesian computation so far is in terms of its real computational speed on specific hardware. So I can tell you in my opinion, what things needs to be done. So in the Bayesian deep learning world, there has been a lot of efforts in terms of pushing the computation methods, right? Reduce its time complexity or say memory complexity to make it run faster. And the people have been trying that very, very hard. But now the game is actually next level, because the LLMs are actually running on basically GPUs, right? And in order to make it run even faster, people actually write GPU specific code like these kernels. Okay, it's not the reproducing kernel space, that kernel, but it's the kernel that is referring to the operators, or like these little kind of algorithms, components that you be used to run specifically on GPUs that will get these kind of further accelerations. So in this sense, I mean, it's also my personal reflection that many of the Bayesian methods, when in design, they are thinking about, in some sense, like the theoretical complexity, which means different kind of operations like matrix multiplication or like factorization or like say multiplication. They view each of these components as running exactly the same speed, which is not true. So really much on GPUs, and especially on maybe even on different type of GPU, let's say AMD GPU versus NVIDIA GPUs. These different operations can actually run in very different speeds. I have my industry friend telling me that at least right now, NVIDIA GPUs are still faster than the AMD one in terms of doing matrix factorization. Okay, so you can see that, right? So this basically means, I think if we want to really implement, let's say, Bayesian methods in a scalable way, I mean, not only to large language models, but just, for very big deep neural networks, right? We need to develop methods that can make not only the theoretical kind of speed faster, but also thinking about really when you implement that on GPUs, really take into consideration that different operations, they do have different costs. And we want to push on this real-time advantage.
Okay. And so do you have something to add about the distribution part of the question, the second question, or?
What is the second question? Can you repeat?
That was if the training data for LLMs come from a single distribution, and if that's the case, how can we detect if a new input is out of distribution?
Okay, so just to say right now, the training, the pre-training of the LLMs, you can pretty much assume that they have trained on the entire web in some sense. Okay, so this means that maybe this question might not be often appearing in the real world, but if you are going to do fine-tuning, right, of your LLMs to some domain-specific data set, or you're going to do this kind of prompting way of prompt some kind of domain-specific data to the language model, then you can still talk about, okay, whether I can detect a data point that is out of this specific domain distribution. I think this will be more practical in terms of applying LLMs. So yes, you can, right? So you can compute this uncertainty, for example, like the total entropy of your predicted distribution, and hope this will work. We recently developed a algorithm to decompose this LLM predictive entropy into the usual concept of epistemic and aleatory uncertainty, and you can really see in our case that the epistemic uncertainty computed from that approach is even better comparing to using the total predictive entropy as a way to detect the out of distribution inputs when you view the in distribution as the fine-tuning data or as the prompting data.
Okay, that's fascinating. I would have so much follow-up question, and actually people have a lot of questions still. But let's call it a show, guys. The coffee is getting cold. Thank you so much, guys. You've been a great audience. Do feel free to come and talk to us, to ask your questions. I see there are at least 2 for you, Melody, so it looks like you won't be able to eat. And there is at least another one about neural networks. So yeah, like please don't be shy, come say hello. I have a few stickers here. If you're interested in working in baseball, that's completely random, but I work in baseball at the Miami Marlins. We're hiring. If you're interested, come talk to me afterwards. But most importantly, please give a big round of applause to our guests today, Ying Jiang Li, Melody Mono, and I said Melody, so that one doesn't exist. Melody Mono and François-Xavier Riol. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.